let's discuss the t-test, one of the most common statistical tests and one that is most often used to compare two groups of scores. In fact, though, there are actually a few different forms of t-test depending on the two groups of scores you're comparing. So the most straightforward version of a t-test is the independent samples t-test. This is what you would use for between subjects experimental designs. Sometimes you'll hear this called independent measures designs, or any other situation where you're comparing two different groups of scores. So for example, you might have a hypothesis about your new treatment, so you want to use inferential statistics on your sample to test a hypothesis comparing treatment to placebo. Or maybe you want to compare the group you assigned to read an angry story to the group you assigned to become relaxed in an experiment in order to make some inferences about anger versus relaxation out in the population. Or maybe you want to compare two pre-existing groups, like men versus women. That would also use an independent samples t-test. So it's not just for experimental designs that are between subjects, but also for totally correlational studies where you want to compare two groups on some numerical variable. The point is, those two groups are distinct sets of people. Each person is only in one group. Each person is only in one condition. And as far as what the calculation is doing, basically it measures the difference between the sample means and does a t-test on that. Which means you'll take a sample of, say, men and a sample of women, and you find the sample mean of each group. You subtract that to see how far apart the two groups are. Like maybe the women group was on average 10 points higher than the men group. Then what you're going to do is count how many standard error of the means that is. Basically, it's kind of like counting how many standard deviations apart those two groups are, but with a fancy way of calculating the standard deviation that takes into account sample size. But the point is, you get a t-value, like say t equals 2, which would just mean the groups are two standard errors apart, two standard errors of the mean apart. And you can look up on a table and find out what p-value that corresponds to see if it's statistically significant, to see if you would be likely to find two samples this far apart if the null was actually true and men and women didn't differ. Now, a slightly different version of the t-test is used when you're comparing two groups of scores that actually came from the same people, or matched pairs of people, we could say. So we call this a dependent samples t-test. This is what you would use for within subjects experimental designs. Sometimes you'll see this called a repeated measures design, where you're comparing two conditions in the same set of subjects rather than two distinct groups of people. Or maybe you could also use this to compare matched or paired subjects. So for example, you might take 50 people and measure them pre-training, and then measure those same 50 people again after the training intervention. So you're comparing their pre-scores to their post-training scores to see how much change there was in that same set of 50 people. But that means each person was measured twice. They were measured in both conditions. That's where the term repeated measures comes from that I mentioned before. And likewise, maybe you have a yelling condition and a praise condition in some experiment you're doing, but rather than randomly assigning people to only one of those conditions, you're going to have all your participants do both conditions. That way you can see for each person how much their score differed in the yelling condition to their own score in the praise condition. You find each person's difference score, we could say, their difference between their yelling score and their praise score. Or another example might be measuring people when they're sleepy, like if you sleep deprive them one night, but then measuring those same people when they're well rested on a different night. It's still the same subjects in both conditions, so you're not comparing one group of people to another, you're comparing the same people in two situations. So what you're really doing is for each person calculating their difference score between the conditions. For each person, how much lower was their performance when sleepy compared to well rested. And so as far as what the calculation is doing, basically we measured everyone's difference score. So we're going to do a t-test on the mean difference between conditions, the average difference between condition 1 and condition 2 across all our subjects. So you just count up everyone's difference score and average those out. And that's it. You've got the mean difference. And our t-value is just going to be counting how many standard error of the means, that is. How many steps of the SEM, that is. Like a t-score of 1.5 would mean on average everyone was 1.5 standard errors lower in the sleep condition than they were in the rest condition. And again, you can look up on a table and find out what p-value that corresponds to see if it's statistically significant, to see if you would be likely to find a mean difference this big in a sample of this size if the null was true, if the two conditions didn't actually differ. How likely or unlikely is it that we would find things this far apart on average? Now, the dependent samples t-test is also used when you have pairs of scores that go together, where maybe people are directly paired or matched in some way such that the samples aren't independent, meaning they are related or dependent. So for example, if we measure relationship quality using a relationship survey and we give the survey to pairs of spouses, let's say in this case heterosexual spouses for this one study, we might compare the scores husbands tend to give, on average, to the average of the wives' scores. But our statistical test has to take into account that these aren't kind of totally different, independent, and unrelated groups of people, but rather each husband score is paired with a specific wife score, and vice versa. Or it could be comparing the extroversion score for older spouses to younger spouses in like a same-sex, maybe age gap relationships, where for each couple you'd get a pair of scores. You're looking at the difference when you subtract the younger person's score from the older person's score. Or similarly, you might measure some numerical variable for a pair of siblings, one score from the older sibling and one from the younger sibling, to see what the average difference score between them is, to see if the older siblings on average are different than younger for this variable. Or the same thing if you get a pair of scores, like one from a mentor and one from their mentee. The point is, these scores go together. They're naturally paired. They're not independent. It's kind of similar to how a within subject design means each condition's scores are paired because it's the same person in both conditions. Here it might be different people, but the scores are paired in some way. They're still clearly related and dependent. But the stats are the same either way. If you're doing a dependent samples t-test, it still performs a test on the mean difference between the levels, between the two sides here. The mean difference between husband scores and wives scores, or older scores and younger scores, or something like that. Okay, so let's sum up the main t-tests. If you're comparing two different groups, use an independent samples t-test. And if you're comparing two conditions in the same group of people, or if you've got two sets of naturally paired scores, like the husband-wife thing, then use a dependent samples t-test. Finally, there is one other t-test you could sometimes use, which is when you're taking just one sample, like just one group or condition. You're not comparing different groups, you're just taking one group. So what you're doing is, instead of comparing one condition or one group to another, maybe you want to see if your group differs from some hypothesized value. Like, does the group on average differ from 0? Or does the group score on average differ in IQ from what we define as sort of standard, normal, average IQ of 100? So you can test if your sample is enough standard deviations away from this hypothesized value for you to conclude that this group differs from that hypothesized value. You still calculate a t-value, meaning how many standard error of the means you are away from the hypothesized value. And again, that lets you look up a p-value to see if you're statistically significant or not. And remember, when you do an inferential stats test like a t-test, the p-value that you can get from that at the end, it tells us if it's statistically significant. Is there a real difference, a real effect? But the important other half of the coin is effect size. After all, statistically significant tells us there is an effect, but it doesn't tell us how big the effect is. So when you report your p-value on a t-test, you would also want to report effect size. And for any t-test, we would usually report a Cohen's d value. Specifically, it's an estimated Cohen's d since it's based on our sample data, and we're using it to estimate our best guess of what the whole population's effect size is. So for an independent samples t-test, Cohen's d would just be the difference between your two groups, and you divide that by the standard deviation. Specifically, this is like the pooled or combined standard deviation between the two groups. That's what you divide by. But basically, Cohen's d is how many standard deviations apart the two groups are. For a dependent samples t-test, it's the mean difference. Remember, the average difference between your two conditions, and you divide that by the standard deviation. So it's just how many standard deviations apart the two conditions are. That's all Cohen's d is counting. For a one sample t-test, it's just how far your sample mean is from the hypothesized mean divided by the standard deviation. So again, Cohen's d is just how many standard deviations away from the target your sample was. It's the exact same concept in all of these and the same way of calculating it in all these cases. You just take the distance, the difference that you found, and divide by standard deviation. Now, before we move on to ANOVA in the next video, how about a quick pop quiz just to practice this stuff? So imagine I'm comparing gun owners to non-gun owners in terms of their income. And I find that gun owners make significantly less. This is just made up, by the way. The question is this an independent samples t-test I ran or a dependent samples t-test? Pause and guess before you unpause. So this one is an independent samples t-test since these are distinct groups of people that we're comparing. How about this one where I measure 5 kids' IQ at age 5 and then I test those same kids again at age 6 to see if they changed. Like maybe I find no significant change in IQ across that time. Did I test that with an independent or a dependent samples t-test? Pause and guess. So this one is dependent samples t-test because each person serves in both conditions. So each score in the left column is paired with the matching score in the right column. How about this one, where we measure 6 heterosexual couples to see who tends to eat the most dessert, wives or husbands, and maybe we find husbands eat more dessert. Which t-test did we use here? Pause and try. So this one is also dependent samples t-test. Even though it doesn't have each person doing all the conditions, it does have matching pairs of scores in a different way, right? This time scores are paired because we're measuring people that kind of come together, so their scores won't be independent. Finally, one more. Let's say we compared restaurant customers who say they were satisfied after their meal to those who say they were unsatisfied after their meal to see which group tipped a higher percentage on the check. Maybe we found no significant difference between those two groups. Did we use an independent or a dependent samples t-test to test that? Pause and try. So this one is independent since each data point comes from a person who is only in one of those groups. A person is either satisfied and thus in group 1 or not satisfied and thus they're in group 2. So this would be an independent samples t-test. But okay. Enough about t-tests. In the next video, let's move on and talk about a similar situation where we want to do the same kind of thing, but maybe we're dealing with more than 2 groups or conditions. In that next video, we'll discuss ANOVA.